Hi scholars, I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day, we care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. All right, so during the last couple of lessons, we've sort of started with our numbers, with our natural numbers. We've expanded that to include integers, so those would be negative numbers and 0 as well. And the last lesson, we sort of had our first glimpse into the role that algebra could play to make claims and support claims about divisibility and about even numbers and odd numbers, right? And essentially to prove that certain patterns that we see are always true. And so proof is a really fundamental idea in math. So we got a glimpse of that. So today we're really going to dig deep into algebra, algebraic expressions and equations and identities. So the first thing is I want to take a minute to think about the history of algebra. So now in school, right, you get up to your 8th grade or 9th grade Algebra 1 class, and it's a lot of solving for x, right? So you're given an equation, you use inverse operations, you get it, right, x alone, you say x, here's the answer, x equals 7, and sort of move on with your life. So historically, that's a fairly recent way of viewing the subject of algebra. So for example, what did algebra used to look like? So there's a great Muslim scholar and mathematician who lived around 800 AD, and this is the way that a solve for x question used to be posed. A square and 21 in number are equal to 10 roots of the same square. And what does that mean? Well, today, what would we write? A square, let's say a square is x squared, right? And, well, and is just addition. 21 in numbers, so the number 21, okay, are equal to, oh, well, that's a pretty clear way we can translate that. 10 roots. So the thing that's the most confusing about this sentence is this word roots. The roots of the same square. So this is what they mean. They mean x squared is a square. A root of a square is the root of x squared, right? This is the square root sign, right? So the root of x squared is just x. So 10 roots of the same square is 10x. So this entire sentence is really saying solve for x. X squared plus 21 equals 10x, right? And we'll learn over summer how to solve these equations, or you may know them already. It's a quadratic equation. We can use some product properties and factor them, and then use a zero product property to find the roots, find the solutions that make this equation true. But just take a minute to read over what the solutions used to look like, right? Take half the number of roots, multiply it by itself, subtract this from 21, right? This is the method that was used to solve quadratic equations around 800 AD. So I just introduced this to everyone so that we can appreciate and be so grateful for the fact that we live in this world as opposed to this world, where solutions were very procedural, as you can see, right? It's basically telling you exactly what to do. It's like a recipe. First do this, then do this, then do this. It's much nicer to be able to sort of use some concepts or some broader ideas about how to solve this equation, or any equation, any quadratic equation more generally, right? That's much more valuable knowledge than how to solve this particular equation. So, a little bit of history. All right, let's move on. All right, so we're talking about expressions, equations, identities. Let's start with x. So, our first question is, what does x mean, right? And the variable x or a or b, any of the variables, there's sort of two general ways to interpret them. So one way to interpret them is an unknown value that's fixed, right? So that would be like in an equation that when you solve it, you end up with x equals blah, whatever it equals, right? It's an unknown value. Another way of viewing a variable like x is a value that varies. So I'm going to just write that down. A value that varies, and that's of course why we would call it a variable, right? And that varies means it can change, right? And you see that interpretation of x lots of times in formulas, or that interpretation of a variable in formulas. So for example, we have our formula in physics that says that force is equal to mass times acceleration. It tells you how to calculate the force in newtons of that object. And here, in this formula, there's no way to say, oh yeah, m, I know what m equals. You're never going to say, oh yeah, m equals 4 or something like that, in the same way that if you're solving an equation that only has one value, right? You could say, oh yeah, x equals 4. So this is not the interpretation of m in this formula. It's just something that represents mass, and the mass could be large, could be small. So it's a value that can vary. Okay, so we have two ways to interpret just a simple variable. Okay, let's add some more stuff to it. So what about if I wrote 2x plus 6? And so the question I could ask is, what is the value of x? And the answer is, that's a silly question. That question makes kind of no sense, because there's no restrictions being put on the value of x here. This right here is, right, an expression. This is an example of an expression. And an expression has no constraints on it, right? So there's no way to say, oh yeah, I know what x is. X equals 4. No, x could be anything in this expression. All right, so let's keep going. What about if I kept my 2x plus 6, and I added, oh, it equals 14. And I said, what's the value of x? Now we're in business, right? Now we could actually solve this equation because we are given a constraint. We're being told that this 2x plus 6 is absolutely equal to this 14. These two things are identical. And so we could solve it. So let's just solve it just real quick over here. 2x plus 6 is 14. We can solve it using inverse operations, right? You subtract 6 from both sides of the equation. I like to put a dotted line where my equal sign is, just so I remember or keep everything on track on the left side or the right side. You get that your 2x is 8, and divide by 2, again, inverse operations, multiplication and division. And finally, we get an answer of x equals 4. So the question, what does x equal? X equals 4, right? In this equation, right? So this equation, if we said, is it true? Is this equation true? The answer is, yeah, this equation is sometimes true, right? When is it true? Well, it's true when x equals 4. When x equals 5, it's not true, right? When x equals 0, it's not true. When x equals my foot, it's not true. But when x equals 4, it is true. So this is an example of an equation that is sometimes true. So let's keep going. What about if I wrote that 2x plus 6 is equal to 2 times x plus 3? And I said, here is an equation. What is the value of x? And you think, oh, wait a minute, I can solve that. So let's actually try to solve that. I'm just going to erase this part right here so we have a little space. And let's try to erase that too. It's kind of ugly. And let's try to solve this equation using sort of what we know about distributive property, inverse operations, and so forth and so on. So great. So we have 2x plus 6. And I say it's equal to 2 times x plus 3. Okay, so I say, aha, I know how to use the distributive property. We did that before, so I have 2x plus 6 is equal to 2x plus 6. Okay, that's fine. Let's just try to maybe get all of the x's on one side and all the numbers on the other side, right? So let's subtract 2x from both sides, and then let's subtract 6 from both sides, and I end up with 0 equals 0. And the question, right, what does that mean, 0 equals 0? Well, that's a true equation. 0 does equal 0, right? And so what that means is that our original equation right here is always true, because this thing right here is identical to this thing right here. It's just another way of writing it, right? It's writing this expression in a different form. Remember, we talked about form a few lessons ago. And so this right here, when you have an equation that is always true, we call that an identity. And identities are always true. Okay, so expressions, we say, are they true or not? It doesn't mean anything. They just are. It's not about if they're true or not. And equations, some equations, right? So this equation in particular, right, it is sometimes true because we can solve it. An identity is an equation that's always true because the quantity on one side of the equal sign and on the other side of the equal sign, those things are identical, right? So you see the word identical inside the word identity. Okay, let's keep going. All right, so here's an example that you can try on your own. So create an equation based on what we talked about that is sometimes true. There are many answers here. This is basically an equation that you can solve, right? So you can end up with saying x equals 5 or x equals 2 or something like that. Many possible examples here. For example, I could say x squared equals 4, and the answer there would be that this is true when x is 2, or x could also equal negative 2, right? Because negative 2 squared is also 4. So this is an equation that's sometimes true. Sure. Create an equation that's always true. So here the trick, you can of course try it. Here the trick is going to be that you want to come up with an expression on one side of the equation. I could say 4x minus 12. And on the other side, you want to make sure that you're preserving everything on this side, that you're just rewriting it in a different form. So in this case, we could factor out a 4, right? And just write this as 4 times x minus 3. This is an equation that's always true, right? This factoring happens, just as a quick review, because this 4x is really 4 times x, and this 12 is really 4 times 3. And we can take that 4 on this part of the expression, and factor it out of each, and what's left over is our x minus 3, which is right there, x minus 3. So just a quick review of that factoring there. And so let's keep going. Do you think it is possible to have an equation that is never true? So we know we found some that are sometimes true, that are always true, but is it possible to have an equation that is never true? So try to create an equation that has no solutions. That would mean it's never true. So take a minute. And there are many possible ways to do this. The easiest way is to take an identity that so for example, we saw earlier in the lesson, this right here, this is an equation that is always true, right? So I can start there and then just change one side, right? So if I do plus 1, right, for example, this right here is an equation that's never true. We can see that it's never true by solving it real quick. So I could end up with, right, let's just do this real quick. Try to solve it, right? 2x plus 6 plus 1. We can subtract 2x plus 6 on both sides. Okay, this is sort of exactly what we were doing before. And we end up with 0 equals 1. And when you do some work and you end up with 0 equals 1, you are on the wrong path, right? So this is an indication that what you started with was kind of garbage to begin with. That this starting equation really has no solutions. So that's one way to come up with an equation that has no solutions. Before we go ahead, I want to just go back right here to this idea of creating an equation that's always true. So in the past, almost every year that this is taught, some students come up to the board and they will say, I know an equation that's always true. It's a squared plus b squared equals c squared, right? Because we all know that equation. So it's got to be always true, right? And so this is, it's not always true. So this right here is an equation that, if we remember, it's the Pythagorean theorem, and it's an equation that relates three sides of a right triangle. So we can say if A and B and C are lengths of sides of a right triangle, right? But that's a big if. If that's true, then a squared plus b squared equals c squared. Yeah, then it's true. But a, b, and c, if they're just any old numbers, then no, it's not true, right? 1 squared plus 2 squared, does it equal 3 squared? No, if we do the math, right? On this side we end up with 5, on this side we end up with 9. No, these are not equal. So this right here is a formula that relates to a very particular geometric situation. It's not always true. It just is true in the case of a right triangle. So that often comes up. I just wanted to mention. All right, so we're going to close out this lesson going through a couple of examples. So let's look at example number 2. Solve for x. We have the equation 3x minus 2 equals 19. So one way of solving this equation is to use inverse operations. So I see that I have a minus 2 here, so I can add 2 to both sides. And this is likely the way that you were initially taught how to solve equations. So you end up with 3x on this side, 21 on this side. And we'll use our inverse operations again. We'll divide by 3. We end up with x equals 7. So this right here is totally acceptable way of solving an equation like this. Of course, we always want to check our work. We can do it real quick. If I plug x equals 7 into the original equation, I have 3 times 7 minus 2. And the question is, does it in fact equal 19? And 21 minus 2, yeah, it does, right? So we can say, yep. That all checks out. It's always a good idea to check your work, just because, I mean, in this problem, it's only 2 steps, but if it's multiple steps, sometimes you miss a plus sign, a minus sign, something like that. So it's always a good idea to check your work. So another way of solving this that I want to stress, it's not necessary in this particular example, but it can be helpful, is to use structure. So let's take a look at what that might look like. So we had our 3x minus 2 equals 19. What I'm going to do is to rewrite 19 so it looks kind of like it's in this form, right? That's what I mean by structure. So what's this form? This form is something minus 2. So how can I rewrite 19 as something, right, minus 2? Well, the answer is I can rewrite it as 21 minus 2, right? That's the same thing. And notice now, immediately, we know, because the minus 2 and the minus 2 are the same, we know that 3x equals 21. Well, yeah, that's where we got to by adding 2 to both sides. So it's another way of looking at it. So let's keep solving this problem using structure. So I have that 3x is equal to 21. But again, I don't want to write 21 as just the number 21. I want to write it using structure. I want to say, how can I make 21 look like 3 times something, right? That's the question. Well, 21, I can make it look like that. I can say it's 3 times 7. So 7, that's the thing that makes these two, on the left side and the right side of the equation, makes them look identical. And, well, okay, so if it's 3 times 7, we're done, right? Because x must equal 7, so because they look the same way. They look alike, and boom, that's exactly where we get to. So it may seem trivial or sort of unnecessary. This is a separate way of thinking about how we can solve equations. All right, let's keep going. Example number 3. The number of grains of sand that blow in your eye during a sandstorm is given by the expression 11s plus 3. So I'm just going to write that down here, where s is the number of seconds since the sandstorm started. So if there are 80 grains of sand in your eye, the question is asking, how long have you been in the sandstorm? So the question is asking us for time, and we know that s is the number of seconds, so s represents time. So we can take that information, and say the question is really asking us to solve for s, right? And we're going to solve for s when this expression 11s plus 3, right, which represents the number of grains of sand, when that expression equals 80, right? Because it's saying if there are 80 grains of sand in your eye. So 11s plus 3 equals 80. So we can solve this using inverse operations. We can also solve it. Let's just solve it really quickly using structure. So instead of 80, I'm going to rewrite 80 as 77 plus 3, because then we're able to say, oh, look, right? That must equal that because they look the same. It's just a plus 3 and a plus 3 at the end. So we have 11s equals 77. And again, I'm not going to write 77. I'm going to write it as 11 times something. 11 times 7 is 77. So 11 times s equals 11 times 7. And we are done, right? Because s must be equal to 7. So s equals 7 is correct. And we will, of course, we want to reinterpret that in the context of the problem. How long have you been in the sandstorm? You've been there for 7 seconds, right? And that's the answer. Okay, let's do one more quick problem. Let's solve for x here. And in this case, we have variables on the left side and the right side of the equation. So I'm just going to go through it fairly quickly here. We, again, want to use inverse operations. Let's get all the x's on this side of the equation right here. Let's get the x's over here, and let's get the numbers over here. So let's subtract 2x from both sides, and we'll be able to subtract 4 as well from both sides. And what do we do when we get that? We have a negative 3x minus 2x. That'll be a negative 5x. These cancel. That's the whole point of why we subtracted 4. These cancel. That's why we subtracted 2x. And on this side, we're going to have a positive 10, right? 14 minus 4 is 10. Let's divide by negative 5. Divide by negative 5. And we end up with x equal to negative 2. Now, we definitely, of course, want to check that. I'll leave it to you guys to check that. So plug in x equals negative 2 anywhere you see an x, and make sure that that equation is indeed true. Great. Thanks so much. Hope you enjoyed the video, and stay safe.